Today we're going to talk about colligative properties. There's a couple vocab words that I'm going to go over. Volatile means easily vaporized or flammable. Mainly it means easily vaporized, but things that are volatile tend to be flammable, so we can throw that in there. Non-volatile is just the reversed. A solute, something that dissolves in water, although it doesn't have to be water, it could be anything, but it usually is water. So when you put these together, we get a non-volatile solute, which is basically a salt or anything ionic. These words are synonymous. Calling something a salt is calling it ionic. These words are going to become important as well in the next unit. Disassociate, if you break the word up, disassociate. If someone is an associate of yours, it's someone you hang out with or are close to. So if you disassociate, you break up. So in this case, we are going to take a molecule and break it up into ions when dissolved in water. That's what disassociate means. An electrolyte is anything that dissolves and disassociates in water. Non-electrolytes, they dissolve, but they don't disassociate, and they don't always dissolve. To figure out if a non-electrolyte dissolves, what you have to do is, if it's ionic, you use table F. If it is covalent, you're going to have to use SNAP and like dissolves like to figure that out. We'll go over more of this later. So that's the vocab that we need. And now, what is a colligative property? What does it do? Well, it does two things. It makes the boiling point of the liquid or the solution go up, and it makes the freezing point of the solution go down. That's it. Those are the only two things that happen. What does it depend on? It depends on the number of dissolved ions or particles, whatever you want to call them, and the concentration of the solution, which will also be affected by the number, basically the molarity of the solution or the amount of water you have it in. So the first thing we're going to look at is just purely based off of the number of dissolved particles. So if we do the dissociation reactions for these, I'm going to show you how they work. C6H12O6, since it is covalent, and it is, you wouldn't know, you don't know how to draw this, but this one I will tell you. It is asymmetrical and therefore polar. It will dissolve in water, but because it is covalent, it doesn't break up. So when you put sugar in water, you get sugar water. It doesn't separate out into ions. So you would get, for every one particle of sugar you put in water, you would get one particle of dissolved sugar. That's pretty simple and pretty straightforward. Next one, NaCl. It is ionic, and when we go to table F, it tells us that it does dissolve in water. So therefore, it is going to not only dissolve, but because it is ionic, it is going to dissociate or break up. So Na and Cl will turn into Na+1 and Cl-1. The +1 and -1 came from oxidation states, which you should already know how to do, and I give it AQ symbols to show that it's dissolved in water. So for every one NaCl I put into water, I get two particles out. So in this case, it would be two ions. Calcium chloride, same thing. For every one of these, it dissolves, it's ionic. Table F tells me it dissolves. When I put it in water, I get one Ca+2 and two Cl-1s. So that is a total of 3 ions dissolved in water. And then this one, Mg3N2, it dissolves and it dissociates, table F. When it does that, it breaks up into 3 Mgs and 2 Ns. The Mgs are +2, the Ns are -3. We would get five moles of dissolved, or 5 particles dissolved. Okay, so these are my number of dissolved particles. There was a mistake there. Now, when we look at it in terms of how it affects boiling point, here's what happens. On regular water, the boiling point of water is 100. The freezing point of water is 0. So if I added glucose to water, its freezing point or its boiling point would be above 100, and it would be below 0. Okay, so it would be in the negatives. Now, you don't know how to calculate just exactly how much above 100 or below 0 it is, and we're not going to learn that. That's a topic we skip. But you just need to know that it would go up, the boiling point would be higher, and the freezing point would be lower. And then relatively, since NaCl breaks up into 2 particles, NaCl would also go up, but it would go higher than glucose, and it would be lower on the freezing end than glucose. And then since calcium chloride breaks up into 3 particles, it would be higher than that and lower than NaCl. And since Mg3N2 breaks up into 5, it would be the highest of the 4 and it would on the boiling end, and it would be the lowest of the four on the freezing end. This is what we call boiling point elevation, because we're raising the boiling point. That's what elevation means. And freezing point depression, because we are lowering the freezing point. That's what depression means. Where do you see this used? It's actually pretty common in the winter. We put salt on sidewalks. If you think about it, the salt is not hot, but it still manages to melt the ice. How does it actually melt the ice? Well, what it does is it takes the freezing point of the ice and lowers it to a temperature that is below the current temperature, and therefore the ice turns into water. And the reason we use it in cooking, we will put salt in water. A lot of people think it's for flavoring. It's typically not, because if you think about it, if you're making pasta and you put salt in the water, what do you do with the water when you're done? You throw it out. And so if you had salt in the water, the salt would go down the drain with the water. That's not really for flavoring. If you wanted it for flavoring, you should put it on after, not before. What it actually does is it raises the boiling point of the water, which makes the pasta cook faster and usually a little bit more thorough. Okay, so now this effect is based off two things. The number of particles, I'm going to use the word moles, we could use the word particle or ion, it all basically means the same thing. The number of dissolved particles and the amount of water. So you want to have the most amount of moles or the most amount of particles or ions in the least amount of water. That will give you the most concentrated solution, and then that's how this works. Now, the comparison that I gave you is assuming we have one of each, and we're assuming we have the exact same amount of water, and so that's how these stack up. The other way these problems can be given to you is molarity comparison. And when you do those, then you have to worry about the amount of particles dissolved, so whichever one gives off the most amount of particles, and simultaneously, you want them to be in the least amount of water. And so that's how you would get the highest boiling point and the lowest freezing point. So there's two ways of doing it. A direct comparison where you're only changing one variable, which is what I gave you here, and then a comparison where you're changing multiple variables. You're changing the amount of material that it's dissolved, the type of material that's doing the dissolving, and the amount of water that it's dissolved in. So then there's three things you have to worry about. You will see those questions on Castle Learning.